Lab reports are going to be due next Wednesday. Okay. I may regret this. Y'all probably don't. But that's going to give you plenty of time to get acid-base right. Okay. Also, we did solubility by video, and I imagine not everybody's watched that because if you come to class, you're forced to deal with the material right there. Okay. In the future, I've got that video up there, and I can ask students to watch that earlier. So for a couple of reasons, we also got the unknown lab, which you need to be getting your pre-lab ready for. And so lab report due for everybody in class next Wednesday. I wish it could be Monday, but we're not here on Monday. Okay, guys? Any questions about lab this week? Any questions about anything before we get going? All right, if you got your lab report in good shape, you have time to go back and look at it again. And okay. There's a handout today. We'll pass it around. Start here. Please make sure it goes all the way around, okay? This way first, and then come back down the other side, yeah? End up over here. Okay? That's perhaps our last handout before test 1. And you also have one that you printed out on nomenclature, okay? Including, that's the alkane chemistry, cycloalkanes. But today, mostly acid-base chemistry. We may get to that other handout. This one goes with that's kind of an outline that goes with that one I sent you by email. Acid-base, where do we leave off at? Questions? Hybridization effect. Bases. Okay, you see the hybridization effect up here? We're looking at 4 main things to consider. Those are your arguments that you're typically going to make. When you assess a problem, you're usually going to be comparing 2 different ones, maybe multiple. You use those 4 arguments. They're both carbons, so you can't say there's any difference in electronegativity or size of the atom here. You got to understand there's no resonance for these lone pairs. These lone pairs are not in p orbitals. What is the argument you could make? The argument is a difference in hybridization here. Okay? And understanding that the electrons are closer to mama, they're going to be more stable and thus more willing to exist like this with high electron density. That lone pair is more stable, okay, than this. Because up here there was no lone pair. When it acts as an acid, it takes on a lone pair. That carbon is able to handle it better because the lone pair is closer to mama. 50% S character. Hybridization. Bases. Okay, I said except an H+, but that's really, I wrote that there so we can say, okay, you said that in Gen Chem, but from now on, the rest of your life, I would recommend never saying that. Instead say, bases take an H. Okay? Like the thief took your bike. Okay? And you can see some of these statements are so introductory that I'm not even going to say them to you. Okay? Just making some statements here. Here we go. Acid-base reaction. Now this is also a problem because whenever we do an error, I want you to say what first? Well, ultimately, you're asked that, would you say
the electrons.
These electrons, these electrons, these electrons, these electrons, these electrons. These electrons. What electrons? Lone pairs I will circle them. These electrons, let's extend that arrow. Okay, these electrons go over and make covalent bond to H. That's what the arrow means, right? The electrons here move away from the H onto the Z atom. I said Z because that's what I showed in my mechanism page, which I said is usually important. It's the same mechanism. Now what does that arrow movement give? The carbon, which has 3 bonds to H, now has made an additional bond to H, and there it is. Now you can just show that as CH4. We got to recognize condensed structures. This is showing 1 bond, the rest is condensed. And then hydroxide. Of course, there's 2 lone pairs here. What does this arrow mean? The bonding pair moves onto the oxygen as a 3rd lone pair. Now charges. Well, you should know that that's a minus, and now this is hydroxide. hydroxide that we want. That's an acid-base reaction, but in this case, this acted as the base. It took the H, right? The thing that supplied the H is the thing that acted as the acid is that. If I could put the H in red, instead I'm going to underline it. There's the acidic H. Now it sits with what was the base. And on any acid-base reaction, an H is being relocated somewhere. And because it's just the H and no electrons, it's called H plus in general. And H plus we call just proton. Because an H plus consists of only a proton. It has no neutrons and no electrons because it's positive. Okay. Strong bases will have high pKa for conjugate acid. You should know that. And if not, you should go back to the very first page and think about your pKa equilibrium. And okay, we'll say that along the way. I make statements. We can always discuss them right here. It's best if we move ahead and then come back and say, okay, does this make sense now? But this is your statement. Okay? Bases don't always have to be an anion. Now, most good bases are anions. Anions, good bases. They want to take an H and go back to neutral. Okay? You see how the carbon went back to neutral after it took an H? But not all bases have to be anions. Some neutrals can be good bases, and the most common would be a nitrogen. Neutral nitrogens tend to be good bases. But that can vary, sp3 being the most basic. We will say that plenty of times. There's also that free information sheet in the back. I'll give you about a dozen key points here if you're looking at that. Okay? It's free information, no extra charge on that sheet, okay? All right? Comes with the price of admission. Here we go down here. We have ammonia in water, okay? These electrons can take an H, same thing. What does this form? The ammonia, nitrogen is now bonded to a fourth H. Nitrogen with 4 H's bonded. It's condensed here, but that's a positive charge. Okay? I'd actually prefer you to draw this out so you can see it. Sometimes if it's very small, though, and written, it's okay. But you need to know structure. And then we're going to form hydroxide. You guys seem to just want to memorize that this is produced. And then half the time you get it wrong. I'm like, there's no hydroxide formed here. Where? Show me. You don't need to memorize anything. You start with your mechanism. Your mechanism shows you what's going to be formed. Mechanism arrows. When we say mechanism, it means the arrows. And as we move to reactions, we have to rely on our mechanism arrows. We don't just memorize. Okay? Like in math, do you memorize every single multiplication problem? Quick, what's 56 times 78? Did you memorize that one? No, but you know how to do it. Okay? Mechanism is how we do it, and we learn mechanistically. So we can do anything. You can do any multiplication problem, right? Okay, let's look at bases. And how do we predict them? It's actually just the opposite, but we still use the same 4 guidelines or arguments. Okay, which is stronger base, ammonia or methylamine it's called? Methylamine. Why? What do you see? What's your argument?
The CH.
Obviously this is new. What can it do? It's an inductive donator, an sp3 carbon. So why does that make that more basic? Okay, y'all heard of ED? No? Okay. Electron density. Because this is pushing electrons this way, there's more electron density there compared to here. More electrons are negative. Okay? And the acidic H is partial positive always, you agree? I mean, that's why we didn't go back there. Why would these electrons want to make a bond to that H? It all goes back to physics. Electrons are minus, and that's a partial positive. Why is it a partial positive? Because of dipole. You see, everything is built in there. That's what it's building. And so you have to see all that. Higher electron density here because of the sp3 donation. That's the argument. There's no difference in hybridization. They're both sp3. There's no resonance. Okay? That's it. Number 2, which is more basic? The first one. So make sure you somehow underline which is the strongest base, okay? However you want to do it. Whatever is clear to you. Stronger over here. Someone says the first one. What's your argument?
Conductive effect?
Perhaps, but it's a hybridization is what a greater one to me. This lone pair is in what type of orbital?
SP3.
sp3. This lone pair is in what type of orbital? sp2. You got to know that. Which lone pair is held closer to mama?
SP2.
sp2, more S character. Well, that's going to be less basic. Okay? You got this acidic H with a partial positive charge over here. Okay? Can you read the acidic H? Here's a lone pair. And I'm okay. Ooh. I am on minus. I see partial plus. Physics takes over and this magical bond. Okay? Here I am. I'm okay. Whew. Okay. Consider this now. I'm going to have to move closer and do all this thing. Also, I'm more attracted to myself, to the nucleus. Well, the nucleus is positive, right? Okay. In the end, the further the electrons are out there, the better they're going to act as a base. These electrons are held closer to mama. Hybridization effect. Thus, this is a stronger base. And what we'll say is an sp3 nitrogen is the strongest neutral type of nitrogen. The next would be sp2, slightly basic. When you get to sp, those are really considered basic. Okay? But you should understand that trend. An sp3 nitrogen lone pair is going to be more reactive and basic. Down here, what's the answer? Most basic. The first one. This lone pair is in what type of orbital? sp3, and this one is p orbital. That one's in a p orbital, right? Have we covered that part? Anytime lone pair, everybody see it's in a p orbital? And a lone pair in a p orbital is not basic. Because that lone pair is busy conjugating. Here we go, I got acidic H, I'm a lone pair. Guess what? Next door is a p orbital, and this lone pair is busy doing this stuff. It's busy with resonance and conjugation. And it's just going to ignore that acidic H. He's already doing something else. Okay? I wrote this. Do you think there's an exception to that? Okay, everybody agree? Yeah, I can think of one right now, but I can't tell you every single exception. All right? Maybe in organic 2, when we look at a certain type of compound, I say, remember, this is an exception, guys. Okay? All right. These are the 90% statements. So this is methylamine is considered a fairly good base. That is not. That's lousy. Nope, not a base. There's no basic atom here. Is the oxygen basic? What do we say were good bases? Anions? Or if it's neutral, about the only thing that's good base is neutral is what?
Nitrogen.
A nitrogen. A neutral oxygen is not a good base. Like water. You consider water a base? It's got an oxygen with a lone pair. No, water is considered neutral. Now again, you got to be careful when you say neutral. Are you talking about non-acidic, non-basic, or are you talking about charged or non-charged? Please clarify that. Which is more basic, okay?
Chlorine.
More basic.
Chlorine.
Chloride? Who says chloride? Okay, who says fluoride? Okay, who did not vote? Who still has not voted? The answer is F minus is more basic. Why? Here, what is the argument we can make? Here I want to talk about size and how does that affect stability. Which is more stable? Cl minus is more stable. Why?
It's larger.
Because it's bigger and the charge is more spread out. If it's more stable, it ain't interested in going to react with the H+. It wants to sit on the sofa and watch Breaking Bad. Okay? It's very stable and happy. So you can look at that in some regard. Now you might say with the F, it's smaller, aren't the electrons closer to mama? And that could be an argument that would get you the wrong answer. I could see if you're really trying to give a good logical argument, this one is a little bit more difficult. The main thing is where I get is stability. F minus is actually a pretty decent base. It's used sometimes as a base. You know, like potassium fluoride. Potassium chloride, you never use that as a base. It's just not basic. We know that. And you can also get the answer by this. Go back to acids. Which is a stronger acid, HF or HCl? HCl is why? Because you look at the conjugate base and you're looking at, what are the conjugate bases in these two?
Minus
These two.
HCl.
Why is HCl more acidic?
Larger.
Because Cl minus is more stable than F minus because it's bigger. Okay? But if you know this, and you can go back to that simple thing in Gen Chem, if it's a more acidic species, what does that tell you about the conjugate base? Yeah. So you can rely on that statement, which does hold true if you know what you're doing. Okay? Which is more basic over here? Oh, this one's easy. This is almost just, you don't have to think over there, right? We've already said enough to get that answer right. A neutral oxygen is not basic. Why is a neutral oxygen not basic but nitrogen is? Oxygen is more electronegative. And what is it? How does it hold its lone pairs? Tighter. Oxygen's a better parent than nitrogen. Oxygen keeps the kids close to home. Nitrogen lets the kids get out there and get in trouble and make bonds. Okay? What about a carbon with a lone pair? That would be even a worse parent, right? Problem is, most carbon compounds don't have lone pairs in the neutral state. A neutral carbon typically does not have a lone pair, but a neutral nitrogen does. This one should be easy, which is most basic. And what's your argument? Inductive. We got higher electron density on that carbanion than the other. Okay. Most basic. We flip this question around. Which of the two is most stable? This one's most stable. This one's the least stable. That's why it's most basic. This one's less stable because high electron density is not a good thing. Things want to be closer to neutral. If we push electrons there and build up that minus, there's a force required for that. Well, that force is there and it's doing it. It makes it less stable, it makes it more basic. It won't say H more. I gotta have an H. Where's an H? Compared to this. Now they're both highly basic. We're not looking at absolute separations, we're looking at relative. Okay? And isn't that what we used above? Now why does it say CH3Li? Because anytime you got a minus, you got to have a plus, right? You can't go to the stock room and say, just give me some CH3 minus. It's going to come with a plus. And the pluses can be what? What are your choices? Well, they're up there. Those are your choices. And it happens that with carbanions, lithium tends to be the most common. Okay. Especially if you bind. Now you can make anything you want in the lab. Okay, questions about that page. Now neutral nitrogen, these compounds are very prevalent in nature. Natural products that contain basic nitrogens. You don't know what a natural product is? It's born naturally in nature, found in nature. Okay? All of these are examples of natural products with basic nitrogens, and those are called alkaloids. What does alkaloid mean? Oid. What's a humanoid? Human like. So what is alkaline? Basic. So what does this word mean? Basic life. They have basic properties. Natural products that are basic life. They're basic life because they have basic nitrogen. Here we go. Ergoline. It's got 2 nitrogens. Which one's most basic? Why that one? Because this one is p orbital and this one is what? Yeah, hybridization effect, or where it would take a long pair. The top nitrogen, the bottom nitrogen is not basic. LSD, remember that compound? It's got 3 nitrogens. Which one? Only one of them is basic, though. Which one is basic? Middle one. That's basic, right? Why are the other 2 not basic? Lone pairs and p orbital. All right. Morphine. Morphine was one of the first natural products ever isolated. Very important compound used over the many years. And still today, because from morphine comes heroin. And Organic 2 will learn how to convert morphine to heroin. Okay? We'll also learn how to make methamphetamine. I think in this class we'll learn how to make cannabidiol, the constituent of marijuana, yeah? So these things can be produced. Mother Nature produces them. See? All right. Nicotine. Which nitrogen is most basic? Yeah, that one. Is this one basic at all? No. Yes. No, it's slightly basic. No, this is sp2, and that is sp3, yeah? Neither one, lone pair is not in a p orbital in either case. Which one's more basic? Yeah, sp3. The other one's no closer because it's 33% S. The other one is only 25% S. That percent S answers a lot of questions. Okay, those are called alkaloids. Have you ever mentioned those in biology class? Okay, there's different classes of natural products. Okay, let's see here. Predict an equilibrium of acid-base reactions. Reaction will favor the side with the weakest acid. Oh, by the way, the quiz will be returned during lab. It'll be much easier to do that. Okay. I know you have to wait a day or two. I posted the video. The high on the quiz was a 10. The low, I think, was 0.5. But not. I did not make a 10 though. So some of you made higher than me. I made a 9 on my quiz, right? Because one of them, yeah. number of pi electrons. I said 12. I don't know why I said 12. Answer is 14. A couple of you have asked about that, yeah?
Yes.
Did I not allude to the the carbonyl at all in the video?
I think you drew
Yeah,
over
you
it
drew
when you were
over it.
doing your p orbitals, and you just kind of went over it.
Yeah, I just neglected to count it. Okay, so I made a 9. I don't mind making mistakes sometimes because you see that mistakes can be made. We need to double check our work. All right. But when I was grading it, I knew it was 14, but I kept like 14. Somewhere in my mind, I still had 12. But it was graded as 14. It's correctly. I didn't have to go back and change anything. Okay, so I'll have to pass those back in lab. We will meet in lab downstairs, right? Okay, the reaction will favor the side with the weakest acid. Side here, reaction side. Equilibrium, which side is favored? What's the acid over here?
Water.
What has the H over here? Right there. And if that was drawn in red, where's that H over here now? Did the base take the H? So those are the two acids. Okay? You call this the acid over here. Over here you would say this is the conjugate acid of the base. Acid, conjugate acid. Okay. Which of those two is weakest acid? Well, I gave you pKa's here. You need to learn 16 from water. That's just hydrocarbon, which was on our first page. Hydrocarbon greater than 40. Which one's weakest? pKa tells you that. So which side's favored? That side. How much is this side favored? By 10 to the 24, which is a difference in your log, pKa logs here. Okay? What is it? How much is 10 to the 24? That's like 100 gazillion. 10 to the 9 is a billion. Keep going. Okay? 100 gazillion. That means at equilibrium you have 10 to the 24 here, and you have 1 here. That's your equilibrium. 1 to 100 gazillion. No equilibrium is ever theoretically absolutely complete. This is pretty much complete. Because if you turn that into a percentage, it's 99.99999999999999999%. Would you call that complete?
Yes.
I would, yes. That is, if you put this near water, it's going to take an H and it's going to do the reaction. What if you take acetic acid and put it in water? Which side's favored? Well, what is the reaction? First off, and we'll do more of this, this is actually the acid. Carboxylic acid about 5, and actually you should know that, about 4 to 5. Okay? And if we showed this, if that's the acid, that means water is acting as a base, and this takes the H, and if it took the H, it would form what? Yes. We can show this out. If we're going to show a mechanism, we need to show a bond. Okay? And let's have water here. We need to show things out. These electrons take the H. These electrons stay behind on the Z atom. What does that give? Well, right here, when this becomes third lone pair, it becomes minus, right? What are we forming right there? Third bond to oxygen, only 1 lone pair. It's condensed, it's a positive charge. You've got to see that structure. It's all from the mechanism. If this is 5, what's the acid over here? Where's the H at? It's now sitting with the water, and it has a pK of less than 0. Which is the weakest acid? 5 or 0?
5.
This is. So which side's favored? This side's favored. By how much? Difference of 5 and 0. 10 to the 5. This side is favored. So let me ask you, if you put this in water, does it completely convert to the anion?
No.
No. It mostly stays like this. So would you consider this a strong acid, which by definition it completely ionizes? Does this completely ionize?
No.
No, it mostly stays in the neutral form, non-ionized form. And that's called a weak acid. Because it is acidic, but it's weakly acidic. It doesn't fully ionize in water, but our pKa's tell us this. Hopefully you've done a good amount of pKa's in like Gym 2. But the above reaction is highly complete. Okay, we're going to have to, what do we have to do here?
Draw mechanism.
Show products and tell which side is favored. Here's what you got to look at. Any acid-base reaction, you got to identify the strongest acid and the strongest base. And those two react. Can you identify strongest acids? We did several examples. Can you identify strongest bases? You used the same 4 arguments. Okay? Here's your paper. There it is. What's the strongest acid in the circle? How do you determine acids? You really want to say, where's the best place to make an anion, right?
Okay.
We're looking for the most stable conjugate base.
Yeah.
Where's the most acidic H in the circle?
Come on, right next to nitrogen.
I got an H here. You think this is an acid H?
No.
If it was, you're going to form, this is going to become O2 minus. That's not good. Over here, we got CHs or NHs. Which one's more acidic? NH. Because of resonance. We actually saw this before. If this is the most acidic H, that must be the base. That's reasonable. Then what? These electrons make bond to H. These electrons move here. Show the product. What do we get?
Water and minus.
How many lone pairs on this nitrogen?
2.
Well, how many here?
1.
1. Day 1, we said nitrogen makes 3 bonds, 1 lone pair. Standard nitrogen, neutral nitrogen. Now it has how many?
2.
2. Where did the other lone pair come from? Our mechanism error. Charge of this nitrogen?
Minus.
Minus, yes. What else did we make?
Water.
Yes. This makes a bond, so the O is bonded to the H, and you have 3 lone pairs, but one of them bonded to another H. Mechanism error. That is water, and it's neutral. Look at the free information page. Usually you're going to have the conjugate acid-base pair. One will be neutral, one will be charged. Charged, conjugate acid is neutral. Neutral, conjugate base is charged. That only holds if you're doing plus or minus 1. If you go to plus or minus 2, then that doesn't hold. Because they both can be charged. And usually we're not going to do that. Okay, that is the acid-base reaction that would take place. So, is this reaction favored?
Yes.
This has a pKa of 8. What's the acid over here? What has the H?
Water.
And its pKa is
16.
Which side's favored?
Right side.
Weaker acid, which is this side. This is favored by how much?
10 to the 8th
10
power.
to the 8. Okay, that side is favored. Thus, we can ask, is hydroxide strong enough to deprotonate succinimide?
Yes.
Yes.
Yeah, it just did, and we see it's favored. We get that right? Acid-base reaction, favored. Below here. Show the next one. Where's the most acidic H on the board here?
Right next to the oxygen.
Well, this is just CHs. And CHs here, but I see an OH. Where's the best place to make an anion? On carbon or oxygen? You see, these are the questions, and the answer leads us here. There's the acidic H. Okay? Now, hopefully this is the base, otherwise it ain't being used, and why would it be up here? Is that a reasonable base?
Yes.
sp3 nitrogen. Let's draw this bond out, right? Anytime you do mechanisms, you draw the bonds out. Now, in a couple of weeks, I'll give you another mechanism handout with more of these points. All right? If you want my advice, and if you want to be able to do this correctly and not get into trouble, these electrons make bond to H, these move here. What do we get?
minus and NH.
Okay. It may take you a little time to draw this. Don't worry about it so much. Get it right. It's the same as over here, it's just now it's O minus, right?
Yeah.
Because here we had two lone pairs. Where did the third lone pair come from?
The bond.
That mechanism error. These are called nitro groups. We'll see them in organic 2. It's a common functional group, but usually it's not included on organic 1's functional group list. Some books do. But it wasn't on our list. Very common, called a nitro group. This is actually trinitrophenol. It's pretty acidic for phenol. What else did we make here?
And plus. NH.
That's called triethylamine, these ethyl groups. Tri-3-ethylamine. What's on the nitrogen now? Bond to H. And what, a lone pair? No, a lone pair made a bond to H. There's no lone pair, for many reasons. That's it. This looks like it should be charged. Yes, it's positive. Because this side is net neutral, so that side's got to be net neutral. You can't just create charge. There you go. There's your acid-base reaction. Which side's favored? What's the acid over here? There, pKa1. What's the acid over here? That is, what has the H now? This. What's the pK of that?
28.
It's approximately 10. I told you right here. This is a pKa. That's acting as a base. So why did I give a pKa? pKa describes acid strength. In organic chemistry, we don't use pKbs. Instead, we give pKa's for bases, but the pKa refers to what?
Strength.
The conjugate acid. The pKa refers to the conjugate acid. So, which is favored, 1 or 10? 10. This side is favored by how much? 10 to the 9. That's a billion. Is triethylamine strong enough of a base to deprotonate this phenol? Yes. There's a couple below for you to do. Comment on this. I should have said it up there. I've already commented on it. The pKa thing we mentioned. The one down here, it's only one molecule. The acid and the base are within the same molecule. It's no different. I mean, these up here could have been connected. I could have connected this to here by some long curvy bond. And then it would have been one molecule. The same thing. Okay? Take a look at those on your own and we'll hopefully find time to come back to this. Because you need to have time to think about, put everything together. And then look at a fresh problem on your own. Okay, next topic is what about pH? I think this is the last main topic of the handout. How will an acid or base primarily exist at a certain pH? There's an equation called the Henderson-Hasselbalch Equation that says this: pH equals pKa plus a log of V over A. V is the basic species, or the conjugate base. A is the acidic species, or conjugate acid. We'll show examples of what we mean here. You got 3 variables. 1, 2, 3. If you know 2 of them, you can solve for the other one. Okay. Now the take home is, if you look at the simple math and know what a log is, if the B component is greater than, higher concentration than the A, the pH is greater than pKa. Or we can say, if pH is greater than pKa, then B will be greater than A. On the other hand, if pH is less than pKa, A will be the predominant. I really should be looking here. Here it's summarized better. Here's a summary. If pH is greater than pKa, B will predominate. if pH is less than pKa, A will predominate. That just comes from your math because, look, what if B was 10, like 10 molar, and A was 1 molar? That's essentially 10, right? What's the log of 10? It's 1. And so, if this is 1, that means pH is less than or greater than pKa. It would be greater because it's pKa plus 1. But the only way you're going to get a positive number here is for B to be greater. If A is greater, log of that number will be negative, and thus it will reduce this number over here. So it's just simple math. Look at it. I gave you the summary take-home. Let's do some examples. How will acetic acid exist in the blood, which is a pH of about 7? What do we need to know? We're essentially trying to solve for B over A. We need to know pH and we need to know pKa. Do we know a pH? Yes, 7. Do we know a pKa? Yes, you should know that, 4 to 5. Here's the main question you ask. By the way, which one of these is a variable for the system? Which one can I change? The pH is a variable. You can't change the pKa of a given compound. What we say is the variable thing. Where does it sit? It can vary. Is it above or below the pKa? It's above. 7 is above. It's greater. It's higher than the pKa. And what does high typically mean in terms of pH type stuff? High is basic, yes. Higher is basic. The pH is greater than pKa. Right? Isn't that what we got here? pH is greater than pKa. Thus, which will predominate? The basic species. That kind of makes sense. The higher is the more basic side. Basic will predominate. So then, which is the basic species? Well, I told you. This is the A and that's the B. How do we know that? The acidic species has the H. The basic species, the H is gone. It has nothing to do with charge. It has to do with if it has the H. Okay? Which one of these species has the H?
The left one.
That one. That's why it's called the acidic species. Which one predominates here? B. So if acetic acid is in your blood, it's going to be predominantly like this. Okay? What's the ratio, though, of the two? Is it all like that, or is it a ratio? Equilibrium. It's actually a ratio, and it is a difference in the two here, 5 and 7. At equilibrium, you're going to have one of these and 10 to the 2 of those. The 2 came from being the difference here. B predominates. That's what the summary told us. Okay, you need to look at this. Let me ask you, what if B and A was equal? 50-50, 1 to 1.
Is equal to
That would be like 10 over 10, which is 1. What's log of 1?
0.
0. If that is 0, pH equals pKa. If you think about to turn that around, if pH equals pKa, they're in equilibrium. It's a perfect equilibrium. 50-50. Okay? If the pH was 5, this would be 1 to 1. Right? Now, in biochem, you will derive that equation. How you get to that point. And we're not going to do it here, but you will have seen it and used it before you get to biochem. Okay, I think below is just something you can read. That's sort of my original free information, but then most of that stuff is now over in the back. We can look at some examples. Here's codeine. Very similar to morphine. Codeine is made from morphine. If you ever take codeine like a tablet, it's going to be given as the hydrochloride salt. Because salts are more soluble in water. Ionic. Have you said that before? Well, this is just showing an acid-base reaction for converting this. Do we have a basic site in this molecule?
Yeah.
Yeah. Can we protonate this? Put an H on it?
Yeah.
We can. What would we want to react with?
And that's it.
How about your favorite acid? And a strong acid would be best. HCl? Here's your mechanism arrow. Yep. These electrons do what? These electrons move here. That's going to give this right. Plus what?
Minus.
CO minus. See, everything's here. How about the equilibrium? Which side's favored? I'll tell you that this has a pKa of about 10. And that has a pKa of minus 5. But that's pKa. What does that actually refer to?
Conjugate acid.
This. Here's your reaction. Which side's favored? -5 or 10? 10. The weaker acid. It's favored by 10 to the 15. That's why you use a strong acid here, which is going to have a very low number. Because we used a very strong acid, that ensures that the other side is favored. You're not going to have anything like, you never have like a -10 here. That would mean that this is a stronger acid than that. You can't have a stronger acid than a strong acid. So you use that, and we made what's called an hydrochloride salt with codeine. Salt being an ion pair. Now we have a pair of ions. The drug is given like this because it's more soluble in water. Sometimes we need to say more, because it may not actually be fully soluble, but for us, we said ionics are going to be soluble in water. I think we also said there's plenty of exceptions. Okay. Now I said 10. Down here I may say 8.2. I rounded off a little bit. Okay, are we ready to go back to here? Can we do this one now? Remember this one? Now this one is pretty straightforward. That is, there's not as many things to consider. Hopefully it's going to be much easier now, right? And what's reacting? What's the strongest acid on the board? That's like duh, right? You got ACL there. That's one of the 7 strong acids. We don't even have to look over here. I don't think. So this must be a base. You see a basic atom?
Nitrogen.
Right here. We need to draw bonds if we're going to show mechanism. These electrons attack the H, these move over here, and we're going to get what? The nitrogen has 2, what is an Me?
Methyl group.
Methyl, just CH3 group, right? Nomenclature video. And what else is on the nitrogen? H. I'm just going to cut that off. Everything else is the same. All right? And what do we need to do here? A positive, yes, that's not a standard nitrogen. And what else is here?
Chlorine ion.
Cl minus. And there you go, there's your product. That's called a salt. It's called the hydrochloride salt of that drug. You got a plus and a minus, just like if I showed you that. That looks like formula, but we also see, when we look at this, we see that that's plus and that's minus, right? And we can put lone pairs, and now we got more formal structure. There's no bond here, right? If you do that, you're wrong. It's not covalent, it's ionic. So you don't need to connect these in any way. It's a charge attraction. That's what an ionic is. By the way, I don't like to call them ionic bonds, because I think that gets you in trouble. I'd rather you know it's not a covalent bond, it's just a charge attraction, Coulombic attraction. Now you can, on the back, and still, yeah. There's one back here for you to try. Yeah? Okay, guys. That's it. Have a good day, guys. See some of you in lab tomorrow afternoon, yeah? And